Back in 1994, software developers were handed this golden rule by a pretty famous group of authors. They're known as the Gang of Four.
Oh, yeah, the classic design patterns book.
Exactly. And the rule was simple: program to an interface, not an implementation.
Right.
And, everyone nods when they hear this. Everyone agrees it sounds incredibly elegant in theory. And then almost everyone fails to actually do it when the math gets genuinely hard.
It really is the ultimate, easier said than done philosophy.
Yeah.
I mean, when you are building a dense, highly complex system, the temptation to just hard code everything together so it barely works, it's overwhelming.
Yeah.
Setting up strict boundaries feels like extra work up front, so you skip it until the entire system just collapses under its own weight.
Which brings us perfectly to the actual focus of our deep dive today.
Right.
We are looking at someone who pulled this off in a notoriously unforgiving environment. We've got a 2026 technical presentation by a developer named Luck036, and it's titled Rest Trait Architecture for Generic Cutting Plane Algorithms.
Quite a mouthful.
It is. But our mission today is to explore how this famously chaotic mathematical solver, the ellipsoid method, gets completely tamed by brilliant modular software design in Rust.
Yeah, the ellipsoid method is essentially a way to solve incredibly complex optimization problems.
Right. And whether you are a software engineer, a math enthusiast, or just, someone who appreciates taking totally chaotic information and organizing it perfectly, this deep dive is going to be a masterclass in how structure prevents disaster.
Because historically, writing code for this kind of advanced math results in a massive tangled monolith.
Totally.
If you want to change how the algorithm handles, say, a specific constraint,
Yeah.
you end up accidentally breaking the mechanism that tracks the algorithm's actual progress.
Okay, let's unpack this.
Yeah.
Because to understand the architecture this developer built, we have to look at how they avoided building that monolith. They broke the system down into 3 orthogonal pillars using what Rust calls traits.
Right. And a trait in Rust is, well, it's basically an ironclad contract. It tells the compiler, hey, whatever piece of code you plug in here, I guarantee it will be able to perform these specific behaviors.
Right.
And in this specific project, which is a crate called allowed goers, the developers separated the algorithm into 3 things: the oracle traits, the search-based trait, and the update by cut choice trait.
Let's try to visualize this for a second. Think of a highly dysfunctional restaurant that's trying to get organized.
Okay, I like this.
So you separate the roles. The oracle is your extremely picky food critic. They don't cook, they don't buy groceries, they just look at the plate and declare exactly what is wrong with it. They just provide feedback.
Right, exactly.
Then you have the search space. That is the kitchen itself. It's the physical container holding the ingredients, the current state of the meal, the cutting boards. And finally, the update by cut choice is the chef's specific knife technique. It's the strategy defining how the ingredients actually get chopped up based on what the critic said.
The restaurant analogy definitely works for the separation of duties. But to make it accurate to the actual math, imagine if the kitchen physically shrank every single time the chef chopped a carrot.
Wait, what?
Yeah. The algorithm works by making the possible space of answers smaller and smaller. It cuts away what doesn't work.
Oh, I see.
So the beauty of the single responsibility principle here is that changing the chef's knife technique, the update choice, doesn't fundamentally break the physics of the shrinking kitchen.
Okay, so the picky critic points out the flaw. The chef changes their knife angle, but the kitchen's walls still shrink the exact same way.
Exactly. This entirely prevents the classic spaghetti code problem. You are completely isolating the math of the cut from the actual state of the container.
But wait, so the oracle doesn't actually solve the problem, it just complains when something is wrong.
Basically, yes.
Because usually when you think of an algorithm, you picture this genius calculator churning out the perfect solution directly. But here, it flips that on its head. It just points out failures until the solution is cornered.
It's a very philosophical approach to problem solving, honestly. You find the truth by systematically identifying and eliminating everything that is false.
Wow.
The most basic version outlined in the text is oracle fees, the feasibility oracle.
Right.
It looks at a proposed point in the mathematical space and asks one binary question: is this feasible?
And if it's not feasible, like if it violates a rule, the oracle returns a cut.
Yes.
Yeah.
And in the source material, a quet is represented by this very specific formula involving gradients, transposition, a beta value.
Heavy math.
Very heavy. But conceptually, just think of it as returning the exact angle of the slice and the depth of the cut. It tells the system, hey, the answer is definitely not in this section. slice it off.
Right. And then the text introduces Oracle Optim, the optimization oracle. And this one seems to hold a bit more memory. Like, it doesn't just ask if a point is feasible, it tracks the best so far objective value, which it calls gamma.
Right, because in optimization, you aren't just looking for an answer that works. You are looking for the absolute best answer. So if the algorithm proposes a new point, and that gamma value actually improves, the oracle triggers what's called a central cut.
Meaning we are getting closer to the center of the target so we can aggressively slice away a big chunk of the remaining space?
Exactly. But if gamma doesn't improve, it triggers a bias or a deep cut. It's essentially adjusting the strategy on the fly based on whether things are getting better or worse.
Okay, that makes sense.
But what's fascinating here is when things get even more sophisticated, you look at Oracle Optim Q. The Q stands for quantized or discrete optimization.
Yeah, this was the part of the presentation that really stood out. The source gives an example of an FIR filter design with discrete coefficients. Why does discrete math need its own special oracle?
Because the real world doesn't always operate on infinite decimal points.
Okay.
If you are designing physical hardware, say the components of a radio antenna, you can't go to a catalog and buy a resistor with infinite decimal precision. You have to buy a resistor that exists in a whole number or on a specific step size on a quantized grid.
Right, you can't have half a physical component.
Precisely. The math has to snap to a grid.
Yeah.
So Oracle Optim Q handles this by returning a quantized solution. But here is the brilliant part. If it makes a cut based on a continuous curve, but that cut falls entirely between the grid lines of the quantized space, the cut physically has no effect.
Oh.
The space doesn't actually shrink.
Because you didn't eliminate any of the actual whole number options. You just sliced empty air between them.
Right, which would normally cause an algorithm to just get stuck in an infinite loop. It would keep making the same useless cut forever.
Yikes.
But this oracle includes a retry logic. It recognizes the cut had no effect and actively searches for an alternative, deeper cut until it actually eliminates a piece of the discrete grid.
That is so clever. And because of the trait architecture we mentioned earlier, a developer can completely swap out a continuous math problem for a discrete one just by plugging in this Oracle Optim Q.
Exactly.
The rest of the engine, the kitchen doesn't even notice the critic changed?
Nope, the kitchen just keeps functioning.
Oh, and before we move on, we have to mention Oracle BS, right? The binary search oracle.
Oh, definitely. It allows you to narrow down the optimal value by constantly asking the feasibility question and effectively cutting the remaining possibilities in half each time. It is incredibly efficient.
So the oracle points the finger and dictates the angle of the slice. But if the oracle is totally separated from the container who actually does the shrinking, where does this cut physically take place?
That happens in the second pillar, the search space.
The arena.
Exactly. And no matter what kind of specific space you plug in, the search space trait guarantees it will track a few standard metrics. It tracks axis, which is the current center of the ellipsoid, and a convergence check measure called TC.
The text lists a few specific implementations of this arena. There's L, the standard ellipsoid. There's L stable, which we really need to talk about in a second, and L1D, which is just a simple one-dimensional space using a radius and a center.
Let's focus on L stable because it addresses a massive problem in computational mathematics. Floating point errors.
Yes, here's where it gets really interesting. The presentation mentions that L stable uses an LDLT factorization for stable rank 1 updates. For anyone listening who isn't a math major, what is actually happening when a floating point error ruins an algorithm?
Think of it like making a photocopy of a photocopy of a photocopy.
Okay.
Computers represent decimals using a limited amount of memory. So an infinitely long decimal gets rounded off. Every time the search space matrix recalculates its shape after a cut, it uses the slightly rounded off numbers from the previous step.
So the tiny rounding error from step 1 gets multiplied in step 2, and by step 1000, the error is so massive the algorithm thinks the answer is in a completely different time zone.
Exactly. The ellipsoid physically warps and collapses because the foundation of the math is just accumulating stress.
Wow.
What L-stable does with LDLT factorization is stabilize that foundation. Instead of just updating the matrix directly and letting errors compound, it factors the matrix into a lower triangular matrix and a diagonal matrix.
Oh, so it sounds like instead of making a photocopy of a photocopy, you are taking the time to go back to the original digital negative to bring a fresh copy every single time. It keeps the image perfectly sharp.
That is an excellent way to conceptualize it. It is building your house on bedrock instead of shifting sand. The matrix properties are preserved, and the ellipsoid remains perfectly positive definite, meaning it doesn't collapse on itself.
But wait, if L stable is the bedrock and it prevents the entire algorithm from imploding, why does the standard L even exist in this code base?
That's a great question.
Because the text notes that both L and L stable take big O of n squared time per iteration. So if they take the same theoretical time, why would you ever use the less stable version?
Because theoretical time complexity, that big O notation, doesn't tell the whole story of real-world performance.
Right.
The constant factors really matter. The standard L uses something the text calls a no-defer trick and a split representation. Essentially, it tracks a scalar value totally separately from the matrix.
So it's just doing less heavy lifting under the hood.
Yes, exactly. Going back to the digital negative, every single time takes more actual processing cycles than just snapping a quick photocopy. If your specific optimization problem is well behaved and you know rounding errors won't accumulate fast enough to matter, the standard L will actually run significantly faster in real time.
Oh, I see.
The architecture just gives you the choice.
It's like choosing between a high-resolution 3D render and a quick tensile sketch. If you just need the rough outline, don't waste the processing power on the render.
Exactly.
And no matter which space you use, the update formula behaves predictably. When a cut is applied, the system updates the center, the matrix, and the scalar. And then, based on the math, it spits out a cut status.
Right. And the three statuses are pretty straightforward. There's success, meaning the slice worked. There's no solm, meaning the math just proved the problem is totally unsolvable, so the program can stop wasting time.
Always good to know.
And no effect, which triggers that retry logic we discussed in the quantized space earlier.
But this brings us to a major logical hurdle.
We have the oracles dictating the cuts. We have the search space managing the shrinking kitchen. If these two pillars are totally blind to one another by design, how do they pass the knife back and forth without accidentally cutting their own hands off? Like, how do they communicate without crashing the program?
This is where the third pillar comes in. Update by cut choice. It acts as a strategy pattern. Historically, in a lot of scientific computing, developers just passed around raw floating point numbers, bare F64 types.
So a function just asks for a number, and you hand it a 5, and the program just has to magically know if that 5 means the angle of the cut, the depth of the cut, or the size of the kitchen.
Yes, which is incredibly dangerous.
I can imagine.
If a developer accidentally passes the kitchen size into the knife angle function, the program happily does the math and outputs total garbage. It might not even crash, it'll just give you the wrong answer, which in engineering is much, much worse than a crash.
So how does this architecture actually fix that? By using new types. Instead of bare numbers, they created distinct named types. Single cut for standard constraints and parallel cut for box constraints. And they tie them together using a generic parameter, which is represented as T.
Oh, okay. Think of these new types like physical Lego blocks. If you have a Lego block with 4 pegs, it is physically impossible to snap it into a slot with 3 holes. It will actively reject it.
Right.
By using that generic parameter T, the developer forces the oracle's cut choice to match the search space bounds perfectly. You literally cannot accidentally use a single cut strategy on a parallel cut constraint because the Rust compiler physically won't let the program build.
This raises an important question, though, because this is what Rust developers call a zero-cost abstraction.
I always hear that term thrown around, but mechanically, what does that actually mean? How can checking all these complicated rules cost 0 performance?
Well, in many programming languages, verifying that the types match happens while the program is actually running. The system uses something called dynamic dispatch, or a vtable.
Try to conceptualize that vtable for us. What does that look like?
Imagine a factory worker who has to stop and consult a massive physical instruction manual every single time they pick up a new tool, just to make sure they are allowed to use it.
Right.
That checking takes time, it slows down the assembly line. That is runtime overhead.
But with Rust's compile time checks?
The manager checks the manual before the factory even opens. Because T is a generic parameter, the compiler resolves all the logic beforehand. When the program actually runs, the worker just grabs the tool and moves at maximum speed.
Wow.
The mathematical lock and key are guaranteed to match, so you get 0 runtime crashes and maximum computational speed.
So what does this all mean for the actual real-world results? I mean, the theory sounds great, but does this architectural strictness actually pay off?
The presentation provides hard data on a recent refactoring of the codebase. Because the architecture was so cleanly separated into traits, the developer was actually able to remove 2 traits entirely: Oracle Fees 2 and Search Space Q.
So they shrank the code base. But did they lose any features by doing that?
None. Because traits can compose and inherit behaviors, they simply added default methods to the existing traits. Oracle fees got a default update method, and search space got a default update. They achieved a leaner, highly capable system with fewer moving parts.
The text also highlights the profit article for robust optimization.
This is a perfect example of composition. Instead of writing a massive new block of code to handle robust optimization with interval uncertainty, this oracle simply wraps around an existing one.
Right.
It adjusts the parameters slightly and then delegates the actual heavy lifting down the chain.
So you are just clicking existing Lego blocks together in a new configuration to get entirely new functionality.
Exactly.
What about execution speed? You mentioned the factory worker moving at maximum speed without the manual.
The benchmark in the presentation is striking. The quantized profit oracle queue converges about 3 times faster in iterations than the continuous variant.
3 times? Why such a massive jump?
It goes back to the physical space. Because the discrete search space only looks at whole numbers, the total physical area it has to search is dramatically smaller than a continuous space that has infinite decimals.
Oh, that makes sense.
But the amazing part isn't just the math, it's that the exact same algorithm engine adapts to this smaller space automatically because of the trait dispatch. No core code had to be rewritten to get a 3x speedup.
And the ultimate proof that this refactoring worked, all numerical regression values were preserved exactly. The math didn't change by a fraction of a single decimal point during all this code cleanup. It's basically the holy grail of software maintenance.
It really proves the core thesis of the presentation. Because of this architecture, the algorithm is generic, flexible, composable, and clean.
So we started with the game of 4 telling us to program to an interface, and now we've seen exactly what it takes to do it right. By breaking an intimidating monolith into 3 modular pieces, the oracle giving the picky feedback, the search space acting as the physical container, and the cut choice acting as the strategic knife, you create a tool that is lightning fast and structurally bulletproof.
It is the triumph of composition over inheritance. You build robust systems by assembling small, reliable, self-contained pieces.
Right.
And by setting strict boundaries up front, you save yourself an immeasurable amount of debugging time down the road.
Think about your own workflow, whether you are coding software, managing a team, or just trying to organize your week. Defining clear boundaries and responsibilities works. But there is a deeper lesson hidden inside the actual math of the ellipsoid method.
How so?
The entire algorithm relies on this concept of cutting away unfeasible spaces. It doesn't magically jump to the perfect answer right away. It ruthlessly identifies what is false, what doesn't work, and it slices those areas away until only the optimal solution remains. So, as you go about your day, we want to leave you with this thought to mull over. If this hyper-complex mathematical solver finds success simply by systematically cutting away what doesn't work, what infeasible spaces or unproductive habits might you need to permanently cut out of your own daily workflow so you can automatically zero in on your goals?